So, we have been discussing the 5 plane lattices in the last class, and we discussed the oblique P lattice. We also discussed the oblique P lattice, we also discussed the rectangular P lattice, and we found that there are 2 ways in which we can represent this rectangular P lattice. One is to show the points along the line of symmetry and show the points halfway between the lines of symmetry, and both these will now give rise to the rectangular P lattice. So, if you consider this point, these 4 points now will define our unit cell, these 4 points will define our unit cell, and this is a primitive lattice. And the two-fold rotation axis will appear here, 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 because any plane lattice will have a two-fold symmetry, and therefore, the plane lattices will always have a two-fold symmetry at the origin and at one unit translation. So, that is already represented. Along with that, we have the lines of symmetry. So, the lines of symmetry will repeat at these positions, and as we discussed, whatever is the symmetry at the origin and one unit translation will automatically appear at halfway point because of the translational periodicity. So, the similar thing happens here. Even though these points are in the middle of these lines of symmetry, the unit cell is still having one point, which is now again a primitive rectangular lattice. So, we can also have another type of a lattice where we have the overlap of the lines of symmetry, the way in which these are repeated. So, we take this unit, the one dimensional unit, overlap this one dimensional unit with this one dimensional unit, and that is represented here. So, we have this line of symmetry, this is the repeat distance A, and this is the repeat distance D. Here the points are with respect to this dimension. So, we have this point, this point, this point, and this point, and between them we interleave this one now. Because of the fact that we interleave this fellow, this one has come in between, and that also has a line of symmetry by definition which we have given here, and therefore, now we see that there are lattice points at these 4 points and also a lattice point in the middle, and this now defines a different kind of a rectangular lattice which we call as the rectangular C lattice. So, the rectangular lattices, there are 2 types, primitive as well as the centered lattice, and this is represented by this picture here. So, what happens is, because of the fact that we have a centered position here, the property of this repeats at the center, and therefore, the property of whatever is happening here will also repeat at the center, and so we get additional two-fold symmetries now placed at 1/4 between 1 and half. The additional symmetries are placed at 1/4, but they are displaced by another 1/4. So, at 1/4, 1/4 we get a two-fold axis, and therefore, this now defines a new type of a plane lattice which is a rectangular C lattice. On the other hand, if we just have these alternate ones, but no occupancy of the middle, this is similar to the one above here, and therefore, we will get a rectangular P lattice. So, F represents a rectangular P lattice corresponding to B. On the other hand, the E represents a rectangular C lattice where we have a centering. I think I should describe this again for the convenience of people who have a difficulty in understanding this. We have in a rectangular system A equals B, A not equal to B, but gamma is 90 degrees. The fact that gamma is 90 degrees will ensure that these two-fold symmetries which came here without the presence of gamma being 90 will always be present at these positions. So, the moment we have a plane lattice, the two-fold symmetries will appear at the origin, one translation along A, one translation along B, and they will also appear along the half distances. Apart from that, the fact that A is equal to B and gamma is 90 degrees introduces a line of symmetry, and this line of symmetry can be now represented in this one dimensional lattice by these points. The same one dimensional lattice now can move the lines of symmetries halfway, and the points of representations could be halfway between the lines of symmetry. Both of them represent the one dimensional lattice, and the corresponding 2D lattices are shown in C and D. Both C and D now represent a rectangular lattice, but this now is a primitive lattice because the total number of points add up to 1. So, the number of lattice points is 1, and therefore, we have a P lattice. We can always interleave this A and B together, and therefore, we can have alternate layers of this line of symmetry and that line of symmetry existing parallel to each other, as is shown in the diagram E. Here we show that the A type is existing in these alternate lines, and the other alternate lines are represented by this B type. And when this happens, you see that this defines a unit cell with A equals B and gamma is 90 degrees, which is a rectangular representation. However, we get a point at the center. In fact, if you look at the most primitive cell that can be generated in this unit cell, this could be here. I will show by marking with the pen what I mean by this. So, if you see this and this defines a rhombus, and in this case A dash and B dash are the two distances, and gamma dash is the angle, and this represents a primitive rhombus. The problem with the definition of a primitive rhombus is that we do not have a value for gamma prime. Gamma prime is not any value. It has to take this value corresponding to the rhombus. And what is the value associated with the rhombus? The value associated with the rhombus gamma can be calculated as A prime plus B prime divided by 2, etc., etc. And therefore, this is not a uniquely defined gamma prime. So, even though there is a possibility of a rhombus being defined here, the most convenient way of representing, because all the symmetry elements associated with this will represent the presence of the rectangular lattice. So, the rectangular C lattice, if centered, will define now this unit cell. This will now involve the possibility of including this particular center as well. So, we have therefore here A, and if this is A, this is B, and this will now represent our unit cell with an atom with a lattice point at the center. So, the total number of lattice point 1, 2, 3, 4 will define 1, and this will add additional lattice point, and therefore, the number of lattice points is 2, and therefore, this becomes a rectangular C lattice. So, the occurrence of the rectangular C lattice is because of the presence of an additional lattice points. Since we have two lattice points here, this can be represented as a centered rectangular lattice, and so we have two types of plane lattices in a rectangular system. So, what is the implication of this? The implication of this is that effectively there are only 4 plane lattices, but then among the 4 plane lattices, which you can call, which we could have called as 2-dimensional crystal systems, there is an additional lattice that is possible, which is the so called C centered rectangular lattice. So, it now makes it possible to have therefore 5 lattices. The fourth one is A equals B. Here it is A and this is B, and here A equals B because it is a square lattice. In square, the gamma is the angle here, which is 90 degrees, and therefore, we get a definition of a square lattice, which is something like this. Now, what is very interesting is to see how these fellows are developing, how the symmetry elements develop in a situation like this. If you look at this particular point, this represents now, because it is a square lattice, it represents a 4-fold symmetry. So, the presence of the 4-fold symmetry up here is repeated at unit cell lengths. Notice that in the case of the oblique lattice and also in the case of the rectangular lattice, the same symmetry element repeated. Here the 4-fold symmetry now is not repeated because of the fact that these two now, which are diagonals, they intersect at the center, and there we get the definition of the presence of a 4-fold symmetry, which implies that we get additional 2-fold symmetries at these half points. Now, why is that? it is because of the fact that if we take now assume that this is also fourfold symmetry, then this fourfold together will not generate the central fourfold. If we want to generate the central fourfold, these have to be only twofold. Think about it. If we have to generate the central fourfold and also the fourfold symmetries at the cell edges, this has to be twofold. It cannot be any other value. If this is also fourfold, then we will not be able to repeat the fourfold here. The redundancy comes from the fact that these diagonals will now represent the central point, and these diagonals now automatically carry the twofold information. And since these diagonals now carry the twofold information, this central now becomes the fourfold symmetry, and as a consequence these directions will have now at the midpoint twofold symmetries. The same argument goes for the hexagonal P lattice, where A is equal to B and gamma is 120 degrees, and you see that the sixfold symmetry goes up in the edges and threefold symmetries develop in these positions where we have shown, and the central between the 6 and the 6 is always a twofold. So, this now of course will eventually, as you can anticipate, will come as an assignment, and you will have to work it out why this now has additional symmetry elements at different points like 1/3 and 2/3. Why the 1/3 and the 2/3 develops could be in the form of an assignment, and this therefore tells us that there are 5 plane lattices. So, what we have learnt in this particular set of discussion is that there are 5 plane lattices, the oblique P lattice, the rectangular P lattice, C lattice. So, we have an additional lattice with a centering which is associated with the rectangular lattice. We also have the square lattice and the hexagonal lattice. Remember, the rotation axis that can be associated with this are the twofold axis up here, twofold axis up there, fourfold axis here, and the sixfold axis there. You also see that the presence of the threefold axis is automatically invoked in the hexagonal P lattice. So, there is no trigonal P lattice, the trigonal P lattice plane, because it is already there. Suppose you consider this as the origin, then you can define a threefold symmetry primitive lattice associated with the plane lattice. So, it is redundant. So, the sixfold is the one which now dominates in this particular occupation. Therefore, there are only 5 plane lattices. So, even though there are, we talked about 7 crystal systems, here there are only 5, 4 crystal systems and 5 lattices. So, among the plane lattices there are 4 crystal systems and in 2 dimensions and 5 lattices. Now, we will see now what happens to the 7 plane lattices, 7 crystal systems, and how many lattices we can generate with the same logic. Before we go further, we will examine in detail the definitions of the 5 plane lattices. This is something which is very important and crucial. You see that in the case of an oblique lattice, the lattice type is P, the point group associated with the lattice is 2. This is the maximum point group symmetry that can be associated with the lattice. But when you come to the case of a crystal, it depends upon what kind of an object is sitting inside this oblique axis. If there is a material which is now containing an object, let us say a molecule, and that molecule has no twofold symmetry, it can still go into an oblique P lattice with a value of 1. So, the possible crystal point groups are 1 and 2. Both 1 and 2 are possible in an oblique P situation, where A is not equal to B and gamma is a general value other than 90 degrees. Having understood that, we have the remaining P and C with the point group symmetry. The maximum symmetry is 2 mm, and then depending upon the type of object we are going to put in the crystal, it could be 1 m or 2 mm. Same logic applies to the square symmetry as well as the hexagonal symmetry. You see that in the case of the square lattice we get a 4 and a 4 mm. 4 mm is a possibility because you remember that we have the Euler's theorem, and once you have the proper, improper, that combination is allowed, and therefore we will have 4 mm. So, in general, the point group symmetry of this lattice is a proper, improper axis combination. And the value is A equals B gamma 90 degrees, and when the value of gamma becomes 120 degrees, we have the hexagonal symmetry. The hexagonal symmetry, as you see, can also have the threefold symmetry, as we saw from the previous diagram up here, it has also got the presence of the 3-fold symmetry, 1/3 removed from the 6-fold symmetry, 2/3 removed from the 6-fold symmetry. We have the presence of the 3-fold symmetries, and the surroundings of these, suppose we call this as 0 0 0 0 0 0. At this particular origin there is a 6-fold symmetry, then the 3-fold symmetry is removed by 1/3. We can always move the origin to the 3-fold symmetry position, then we will invoke a 6-fold symmetry because of the presence of the 2-fold at the center of this unit cell, and therefore we have these both the possibilities coming up here, the presence of 6-fold as well as a 3-fold. So we can therefore have objects which belong to the hexagonal symmetry, we can have objects belonging to the trigonal symmetry, both going into a hexagonal small p. The small p and the small p tell us that these belong to now 2-dimensional lattices. P represents a total lattice point of 1, C represents a total lattice point of 2. So the number of lattice points in a rectangular C is 2. The point group symmetry is different from the number of lattice points in the lattice. So the lattice now decides how many combinations of symmetries it can have because of the presence of either a P or a C. In addition, we have these presence of symmetry elements, and therefore the objects now which find themselves inside these unit cells will have to look at both the point group symmetry as well as the lattice symmetry. So the presence of the lattice symmetry in conjunction with the point group symmetry, and of course the nature of the material which goes into this lattice, all these combinations will decide what kind of a symmetry one has to take in this particular case. Extending the same logic of finding these symmetry elements, and we saw that there are 5 plane lattices. Since there are 7 crystal systems, these 7 crystal systems now will generate 14 lattices, just like the 4 crystal systems in plane lattices generated 5 lattices. Here the 7 crystal systems will generate 14 of them, and these are referred to as the Bravais lattice. It's after the name of the person who discovered this, and this therefore now represents the third dimension, the 3 dimensions. And then we see here the cubic system. In the case of the cubic system, we therefore have these points. These are the lattice points. Please note that these are lattice points and not atoms. There is always a confusion. So we should remember that we have not brought in any realistic atom or molecule in our discussion so far. So the points which are appearing here are the lattice points. So the lattice points therefore now represent the presence of a primitive lattice, because here now it is 3 dimensions. So each point will now represent 1/8. So the total number of this will be 1 2 3 4 5 6 7 8 multiplied by 1/8. So that will make it 1. So the primitive lattice always has 1 lattice point. We can have the center of the cube centered of the cube located in such a way that we will have what is known as an eye-centered, the body centered lattice. So the cube is up here, which represents 1 lattice point. This one represents the second lattice point. So the number of lattice points in a body centered cubic system is 2. If we can have also the each and every face centered, we will have 4 possible positions in which we can have the occupancies defined, and therefore we have the lattice points at the corners giving 1 lattice point. In addition, the faces give half lattice point. So since there are 3 faces, half will add up to 3. So 3 plus 1, therefore there are 4 lattice points associated with the F lattice. No other possibilities exist in case of a cubic system, which is the highest symmetry system. In fact, I should have shown you the other way around, these 14 Bravais lattices. I purposely showed the cubic one to show the complexity of the situation. Now we will look at it in a simple way. The simple way is that we have a primitive lattice which is represented by P. We can have the C side centered lattice, which is the case with a monoclinic system, because the monoclinic system here now can have, since the angle is 90 degrees, the alpha and gamma are 90 degrees. Because of that fact, we will have this as a possible C centered primitive lattice. So since it is a centered primitive lattice, it could be along C or A or B, but in this particular example we have a C centered lattice. That means there are two lattice points associated with the monoclinic symmetry. So triclinic symmetry always has one lattice point. Monoclinic symmetry, depending upon the case whether it is primitive or centered, will have 1 and 2. A hexagonal system always has only one lattice point. A trigonal system always has only one lattice point. The most common one is the orthorhombic system, where we have 4 possibilities. One is the lattice centering. Of course, in this particular case A, B and C are not equal to each other. So when we have a C centered lattice, we will not have the A and B centered, and therefore we can have a single face centered lattice, which is represented as C. We can have all faces centered as well, which is referred to as F. We have the body centered lattice, which is I. The orthorhombic primitive is also possible. So if we count the total number of all these, which now will account to 14 lattices. So we have 7 crystal systems classified into 14 Bravais lattices. I have got another illustration which is much more simple and straightforward, and this is drawn in projection. So I have drawn the 14 Bravais lattices in projection, and this drawing will clearly tell us how we can arrive at the 14 Bravais lattices. We always want 2-dimensional representations. So here you see that in case of the triclinic system we have only a primitive lattice. In case of the monoclinic system we have the primitive lattice. Now why did I show like this? Because I am now showing the angle beta. This is a C diagram. In fact, this is to show that the C centering can be done in this particular projection. So this is P, the primitive lattice. This is in this case it is A here and C there, and this angle is beta. In this case this is C here and A there, and that angle is beta. The C direction is centered with respect to the lattice centering. Therefore we have 2 plane lattices associated with monoclinic, P and C, and therefore we have P and C lattices coming in 3 dimensions as well. So triclinic has one Bravais lattice, monoclinic has 2 Bravais lattices. Orthorhombic will have 4 Bravais lattices represented in 2 dimensions here. Tetragonal has 2, trigonal has 3, tetragonal has 3, orthorhombic, the tetragonal has 2, cubic has 3, hexagonal has 1, and this is a very special case, as I mentioned, when A equals B equals C, alpha, beta, gamma are the same value, then we have what is known as a trigonal system. This diagram is in conjunction with the diagram we saw just a few minutes ago. In respect to this one, you see that there is a 1/3 and a 2/3 3-fold rotation, and that is what is depicted here in 3 dimensions as well. So there is a 1/3 and a 2/3 3-fold rotation that is present in a rhombohedral system. So there is a 3-fold axis which goes along the diagonal. So if you take a rhombohedral system and put it along the diagonal and rotate that one in such a way that we can rotate it in such a way that the angle becomes 90 degrees, we will have a cubic system. A equals B equals C, alpha, beta, gamma are 90 degrees. So this therefore now defines the 14 Bravais lattices. So we have 32 point groups, 7 crystal systems and 14 Bravais lattices. So obviously the next step is very clear. We have to take these symmetries into account. We have to take the translational periodicity into account. We have to take the crystal system into account. We have to take the 14 Bravais lattices into account, and then distribute the 32 point groups among all these crystal systems. When we do that, the point groups now will align with respect to these 14 Bravais lattices and generate what is known as the 3-dimensional space groups. That is because now in space these symmetries get redistributed. How in space the symmetries get redistributed we will see as we go along. And now before we go further, you remember that we decided to see everything in 2 dimensions, but it is not always possible to see everything in 2 dimensions, because we saw the Escher's diagrams, we understood the concept of periodicity from Escher's diagram, and we had those objects repeating themselves, generating the periodicity, generating the symmetry elements and so on. And then we have to look into the aspect that how one can really look into 3 dimensions, and this is in real situations. In real situations we will have a crystal. The crystal have different kinds of faces. So these different kinds of phases in the crystal have to now be inscribed into a highly symmetric spherical system. So a sphere is the most symmetric object. So we take this sphere, which is the most symmetric object, take the crystal and insert it inside a sphere. In other words, you describe a sphere passing through these points, which I will state it here, and you will get this sphere. Now we take the center of the crystal and draw directions to various planes about which the crystal has grown. This is a very beautifully grown crystal. Not always the crystals are so good, but in this example you see that we are drawn from the center here perpendicular radial direction. So the radial symmetry of the crystal gets represented here. Why do we represent the radial symmetry? Because the radial symmetry is the one which is most common with respect to spherical objects. For example, if you put a center here, all the symmetry elements now associated with this particular sphere can be along the radial directions. So if the crystal has a certain symmetry, the morphology, external morphology has a certain symmetry, that symmetry can be fitted inside this stereographic projection. I will just digress a little bit at this particular point, because we have to see why stereographic projection is very crucial in looking at crystals. And this is in fact the way in which crystallographers practiced and identified all the symmetry elements associated with the crystals. Nobody did X-ray diffraction in those days, because X-ray diffraction was discovered much later. All these concepts of point group symmetries and space groups and so on were kept and derived way back in the 18th century, in the 18th century, 1735 to be exact. In that particular year, it was already shown that there are 32 point groups, and because of the fact that we have now crystalline objects which will now displace these point group symmetries in the lattices, the combination of the lattices and the point group symmetries will give rise to 230 space groups. So all these were worked out much before. So we have to find out how they would have worked it out. Not that we are going to do it this way, we are going to actually use X-ray diffraction techniques, which is an experimentally reliable and developed technique in recent years. In fact, X-rays were discovered only in 1900 by Rontgen, so only after that time. But before that, all the space groups and all the presence of point groups, space groups, etc. were already established. So how was it done? It was done by looking at crystals. And people got hold of very large crystals, large size crystals, so that they can hold it in their hand, and then examine the perpendicular faces, the perpendiculars to the faces, make an impression of that onto a sphere, and on that sphere we can mark the intersection point. So if this is the point which is up here, we mark the intersection point by an open circle. Now I will define what is this open circle and closed circle in a minute. Before that, as I mentioned, we will digress a little bit. We have a similar situation in case of Earth. We have a three-dimensional object. Earth is a three-dimensional sphere. And when we want to study the geography associated with the Earth, we do a different kind of a projection. That is not a stereographic projection. We do what is known as a Mercator projection. In that projection, what we do is we take our Earth, the surface of the Earth, hold on to its diameter, and then press the Earth. It is like taking an orange and press it. Of course, don't do it because it will squish and spread on your dress, but essentially you take this orange diameter and press it like this. And when you press it like this, it flattens out. And the flattened out is your map. So then you take out the regions of what you would like to inspect in this flattened out map. If this is on this side, we will examine those ones. Both northern hemisphere and the southern hemisphere units will be represented, and also the northern hemisphere, southern hemisphere units will be represented on the other side. Essentially, we have to then open it and spread it. This is the diagram you will see in all atlases. So you have pressed it, opened it, and spread it around, and therefore you see the Americas on the left side and the rest of the world on this side. Americas are always separate. So that is what we will see. And now we want to determine the distance between Mumbai and Bangalore, as we discussed earlier with respect to this diagram. So this diagram is telling us, is it clear, this diagram? So this diagram is telling us that the story of Atlas. This is a Greek mythology. The Atlas is carrying the earth on his shoulder, and these two angels want to measure, just like us, the distance between Bangalore and Mumbai. So they are holding this divider, and then this angel, the third one, is helping them out by shining light on this, so that we get a projected image of the surface of the earth. And this is on the ground, and therefore it is two-dimensional, and they now measure this distance and have a scale factor which will work out to the corresponding distance between Bangalore and Mumbai. Now there is a flaw in this particular type of projection, because it depends upon on what point on the surface of the earth we have done this projection. So that way this projection is not a very convenient way of looking at actual systems. In other words, suppose I, instead of taking this equator and pressing it, suppose I take let us say, in fact when I visited New Zealand, this is what I saw. You take New Zealand as this part and compress the rest of the earth on top of New Zealand. New Zealand, as you all know, is the size of our state Karnataka. But when you do this kind of an operation, New Zealand will appear very, very huge. With respect to New Zealand, India will appear very, very small. It may be a little bit of a short length, and of course UK will appear as a point. That is not true, but this is what happens in these kind of projections. So we need to find out a proper way of generating the projection diagram, and that is where the stereographic projection comes in handy. So what we therefore do is we draw all these radial lines with respect to the center passing through the plane of various planes. So that the crystal is made up of various planes. This is, let us say, a diamond. Many of you wear diamonds, many of the students wear diamonds, and the diamonds have got very nice lustrous planes. So from the center you draw these normals. The normal to the plane is the one which is now collected on the surface of the sphere. So we are not now compressing or pressing the sphere, it is remaining as such, and then we do this projection. So when we do this particular projection, what happens is that we will have points with respect to the northern part of this crystal. We also have points corresponding to the southern part of the crystal. So if now we see the northern part of the crystal as is shown here, if there is a point P on the northern hemisphere, we take the south pole and connect it to the to the point P and represent this little p in the equatorial plane as a point, as a closed circle, a little closed circle as you see here. This is the point P, which is now the representation of the projection of this particular point onto the south pole. A similar construction is done with respect to the north pole, and I think we will stop here.